Okay, welcome to chapter 27, and before we start talking about inference with regression lines, we need to refresh our memories as far as regression lines go with the scatter plots and regression and correlation. Okay, so here's a scatter plot. It's measuring they're measuring cardiovascular fitness, and they're looking at how that relates to the athlete's performance on a 20-kilometer ski race. So the x-axis is the treadmill in minutes. That is the explanatory variable. And the y-axis is the ski time, and that is the response variable. Okay. So the next thing we need to look at is the computer printout. So all this information has been put in a computer, and then it prints out this information. Right here where it says, looks like coefficient and predictor, this is going to be where our y-intercept and slope for the regression equation come from. The y-intercept is where it says constant, so that's 88.796. And the slope is the negative 2.335. Okay. All right, so writing the regression equation, remember this is where we wrote y hat, so we need to write what the predicted ski time is. So the ski time, because remember we're predicting what we think it is. Okay, the points here are what the observed values were, and when we draw in this equation, the linear squares regression line, we're drawing in what we expect the values to be. So our expected values end up being the predicted values. It's the same thing. So our predicted ski time, we put the little hat on there, and it equals 88.796, which is the y-intercept, minus the slope, 2.335, and then my x value is the treadmill. Oh, it doesn't quite fit in there. Treadmill. Okay, so we need to make sure that we're writing the words and not just x and y. So interpreting the slope in context, remember that the slope of a line is the change in y over the change in x. So what we're saying here is that for each increase of 1 minute in treadmill time, for each increase of 1 minute in treadmill time, excuse me, the model predicts a decrease of 2.3355 minutes in ski time. Okay, so where is this coming from? The increase of 1 minute is because the slope is really over 1. It's over 1. And we're saying that it's what the model is predicting, important words to have there, and it's a decrease of that many minutes because the slope is negative. Okay, all right, so here's another example. So my suggestion is that you pause the video, fill out what these answers are, and then start the video because I'm going to just write in what the answers are. So the slope, y-intercept, left-hand span, predicted value is equal to this. Okay, all right, so the slope in context. For each increase of 1 unit, because we don't really know what that is, 1 unit in right-hand span. We predict an increase of 0.9383 units in left-hand span. Okay, I'm going to change colors so I can fit this in here a little bit better. Okay, the correlation coefficient is going to be the square root of this. They don't really give us the value here, so we take the square root and we get R is equal to 0.9497. And the correlation coefficient is telling us that there, remember, the correlation coefficient can be between -1 to a +1. The closer to 1 or +1, 1 or -1, the stronger the correlation. And we're just saying that there's an association. We're not saying that anything is caused by anything else. Okay? So being that it's 0.9497, which you would write, is that there is a very strong, so we're first saying how big the number is, positive, because the number is positive, so very strong positive association, that's the word, between right-hand span and left-hand span. Right-hand span and left-hand span. Okay. Change colors again. Okay, now we have R squared. So R squared is obviously the 90.2% or 0.902. Okay. So we would say that 90.2%, and remember that the R squared is describing the variability. How much did the observed values how much does the observed values change from the expected values? Okay, but it's talking about variability. So 90.2% of the variability in left-hand span. So you're just copying these words down, and you just have to remember exactly how to write these. Okay, it's the writing and the responding in the answer that is what is important. Okay, there's no math involved here. 90.2% of variability in left-hand span, I left the word out, left-hand span can be explained by the linear model for right-hand span. Right-hand span and left-hand span. Okay, so the R is describing the association. The R squared is describing how much or what percentage of the variability from the left-hand span, because that's our predicted Y, and how much of that can be predicted by the linear model that is given to us, that we created, or in this case was given to us. Okay, that's what the R squared does. The variability in the left-hand span, the Y value, can be explained by the linear model that we created. Okay, so the next is the standard error. Okay, so and we've talked more about standard error than we did actually in this section. So this would be a little bit easier to explain. Okay, so the standard error doesn't have a sub E, it just is S. Okay, but that is the standard error. So we're saying that that number, 0.6386 units, and remember that the standard error is describing the difference from the middle, or how far away, how far spread out is the data. Difference isn't really the right word. Okay, so 0.6386 units is the typical amount that the predicted left-hand span deviates or is different from, remember I said I didn't really like that word different, it changes. That's really what the word deviate means. Deviates from the actual left-hand span. Left-hand span. Okay. All right, so that's what it's saying. So the standard error is how much does it deviate. So the typical amount that the predicted left-hand span deviates from the actual left-hand. So what's the difference between, I know I keep using that word, from the predicted left-hand from the actual, and that's what this is saying, 0.6386 units. Okay. Okay, so here's another one. What I think I will do, instead, to make this video a little bit shorter, because it's really the exact same thing, is I want you to write this. I will post the answers, and then you can go back and check your answers with this one to check to make sure that you're doing this one right. Okay, let's go on to the next one. Okay, the next example needs you to have your calculator out, so no calculator was needed in that one. Okay, so I want you to pause the video, and you're going to enter anxiety level into list 1 and math test into list 2. And I'll give you a chance to read this and then enter that data. Okay. All right, so now that you've entered the data, okay, so I took some screenshots of what we're going to do next. Actually, let me go back to here. Sorry about that. Okay, so enter the data in your calculator and make a scatter plot. Okay, you might not remember how to make a scatter plot, so that's why I have these pictures on here. Okay, so on your calculator, above y equals is where it says stat plot. So second y equals, your stat plot screen will show up. And you want to make sure that it says stat plots. All of your other plots must be off. If you have something in y equals, just clear that. So you just push y equals and clear. And you want to make sure that stat plot 1 is on. Okay, when you click here, you end up with this screen. So you want plot 1. Click on the scatter plot and make sure it's L1 and L2, and then make sure you press zoom 9. Okay, if it comes back with an error, either maybe you might have not the same numbers of pieces of data in list 1 and list 2. Make sure that is corrected. Also, if one of your plots are on, it won't come up with the scatter plot. Okay, so there's your scatter plot. Okay, so does there appear to be an association between anxiety level and test score? Describe what you see in the scatter plot. And when we did this, we had several pieces of data that were pieces of information that we needed to use to describe the scatter plot. Okay, so here's what we want to write. So there appears to be, this is very mechanical, this is what you have to write. So when you're looking at the scatter plot, you should see there's a weak association. They're not forming one consistent line. Okay, it is negative. If I drew a line in here, it would be negative. And it looks like it's pretty much that I could draw a line through here. So those are the three things that we want to write about. Okay, there appears to be, a weak negative association between anxiety level, you need to write it in context, between anxiety level and test scores. Okay, and that it is roughly linear. That's really all you need to write. Okay. All right, find the correlation. So we might have to go back and remember how to do that too. Okay, so we go to calculate. So we push the stat button over to calculate, and we want to go down here to linear regression. Okay. If you have the older calculator, you're going to want to make sure when it pops up that you have L1, comma L2. If it looks like this, you don't need to worry about it. X list is L1, L or Y list is L2. And when you push the button, you come up with the linear regression line. So we have the slope. Oh, that's right. I remember actually the one that I keep using, it's backwards, but if you scroll down a little bit more on your calculator, this comes up backwards. Not backwards, but B is first. Okay. All right. So 91.658 is our y-intercept. Negative 4.486 is our slope. Here's r squared, and here is the information we were looking for. So here's r. Okay. So we're going to use this in the rest of our problems, actually. Okay. Find the correlation. So it is negative 0.525. What does the correlation indicate? Okay, so this, remember, it's between negative, closer to -1 would be stronger association. So this is kind of a moderate association. Okay, so we'll say that generally, is that saying not, you know, it can happen. Generally, lower anxiety levels are associated with higher math test scores. Okay, so generally speaking, it's, you know, it's not lower because it's negative. That's why. Okay, all right, r squared. So r squared is also on that screen. So r squared is 0.2756. And it says, here's another way to write it, the model accounts for 27.6% of variability. Oops, spelled that wrong. Of variability in math test score. Okay, so just like on the other paper that we had, that's how we're going to write that. Okay, so the r squared model accounts for 27.6% of variability in math test score. Creating our linear model, so we want the predicted of math, so math hat is equal to 91.6583 minus 4.486, and that is anxiety. That's an N. Anxiety that goes in here. Okay, so is the linear model appropriate? And create and discuss the residual plot. Okay, so let's go back to our computer screens here. Okay. All right, so this time, and I put it in a different one, it doesn't really matter. You need to have one plot, you could go back to the first one, that has your X list and also the residuals. The residuals won't pop up on your calculator unless you've done the linear regression line. So you have to do that first. So how you get the, so X list is list 1, Y list is residuals. On the TI-83, you'd have L1, comma, and then I'll show you how to get the residuals. So you go to list, second stat right here, second stat to get to the list. Names, you arrow all the way down till it says residual, and the residual will pop up in here, or on your computers, on your screen it'll pop up. Okay, zoom 9. Zoom 9, and we see the residual plot. Remember, we want it to be scattered. We don't want any line to be formed. Okay, so this is fairly scattered. There's a couple of lines here that are kind of right near each other, but generally speaking, it's scattered. Okay, so we're going to go back here. Okay, and we're going to say, yes, it's appropriate. The residual plot has little scatter. Okay. All right, and then we could talk about the r squared. Okay, however, the r squared value, because it's very low, makes the model a poor predictor of math test scores. Okay. Okay, so interpreting the slope of the line in context. Okay, so for each additional unit of anxiety level, so each additional unit of anxiety level, the model predicts a decrease of about, because it's negative, that's why, a decrease of about 4.5 points in math test score. Okay. All right, the y-intercept, we didn't do that yet. Okay, so the y-intercept is when the x, or when the explanatory variable is 0. So what does that mean? Okay, what does 91.6583 mean? Okay, so when students have 0 anxiety, then their predicted score is 91.685. That's what that means. Okay, so when students have an anxiety level of 0, they are predicted to have, you just have to write this in the context of the problem, they are predicted to have a math test score of 92. That's what that means, okay? All right, so does this prove that anxiety interferes with student performance? Okay, so interferes with is implying causation. So we have to say no. Correlation does not imply causation. Okay, we can't do that. All right, so we have many lurking variables. Okay, the lurking variables are other things that could cause the student performance. Okay, the student wasn't well prepared. The test was out of the student's ability level. There are lots of lurking variables. So a better answer to this would be to name a few of those lurking variables. It is possible that the math test score is affected by, and then you could name a couple of those. That would be a better answer for those. Okay. All right. So all of this, the calculator work, all of the explanation and answers, that will all lead us into our conversation about how we make inference from these regression line equations. Okay, that's it. So make sure you have these answers filled in and that you can start being able to write them this way.